So let's start the recording. This is the 11th video for this linear algebra series following Sheldon Axler's book. So today we will cover diagonal matrices, and then we define the space of eigenvectors. Last time we covered eigenvalues and their existence, then the eigenvectors, and then we have a upper triangular matrices and their relation to eigenvectors and eigenvalues. We will use some theorems from that section of our course and apply it here later. So now let's start. So first is we have diagonal matrices. So diagonal matrices, and then we have, I will just give you a form here. So the form is the following. We get, say, A1 up to AN here, and then 0 here and here. 0 everywhere except the diagonal. This is diagonal matrix. Example is the following. In this example, we will use this 0, 0, 0, and then 0, 0, 5. This is a diagonal matrix. Of course, a diagonal matrix is upper triangular, and in this sense, this has more zeros than the upper triangular matrix because only the diagonal is non-zero. All right. So if an operator has a diagonal matrix with respect to some bases, then the entries along the diagonal are, of course, as we have before, the eigenvalues of the operator. And this is from the previous theorem that we have. Now let us define the following. We will, here we get a linear operator, the vector space V. And then we have the lambda in F. We call the eigenspace, or the space of eigenvectors, T, corresponding to here, lambda is denoted and defined as follows. So here E, and then lambda, and then we have the linear map or linear operator T. This is basically the null space or the kernel of T minus lambda I, where I here is our identity operator on V. So the identity operator just maps V to itself, the small v to itself. So in other words, your this one is the set of all eigenvectors of our T corresponding to our lambda here in F, along with the 0. Of course, 0 is always this is a trivial one. 0 vector. Here, this is sometimes I just write it, sometimes I write it emphasize. This is a vector, but this is clear from the context by some abuse of notation. Okay. So for linear operator T and lambda, the eigenspace is a subspace of V, and then the definitions imply that lambda here is an eigenvalue if and only if. So I will state this as a remark. Your is a subspace of our vector space V, And then another remark is lambda is an eigenvalue if and only if your eigenvalue of t, if the eigenspace here is non-trivial, meaning it is composed of other of vectors aside from zero. Let us consider an example. So let us consider our original sample earlier. This is from above. So this is the matrix. Suppose this is the matrix of our linear operator T with respect to some basis V1, V2, and then V3 of our vector space V. Then what can you say about what is the eigenspace associated to lambda? Here we know that we have 5 eigenvalues, namely the diagonal. So lambda 1 is 8, lambda 2 is 5, and lambda 3 is also 5. So maybe I'll just call this lambda 2. There are only 2 eigenvalues, 8 and 5. So how do you describe the eigenspace? So it's in the module. It's like there are ways to do this. Sometimes if you are already familiar with the computation in matrix form, then you have the concept of free variable. But in the book, we are using the language of linear map. So here we get, so for lambda equal to 8, we will compute our null of t minus lambda I. So this null space is the following. So we get 8 minus 8, and then we get 5 minus 8, and then 5 minus 8 here, and all the rest 0. So this is our t minus lambda I. And then we want to find, this is the matrix of t minus lambda I, and we want to find our null space. Maybe I'll consider in using the language of linear maps. We can compute this by using our eigenvector. Then this matrix here, if you have here 8, 0, 0, 0, and here 0, -3, 0, and 0, 0, -3. And then if you have an arbitrary A, B, C vector, you map these to, like the null space. Then you get -3b equal to 0, and then -3c equal to 0. And then this means that our b is 0, and then c is 0, and then here a can be any value. So that means that our null space is just when I can vect the null of t minus 8i is just A, and then we get here 1, 0, 0. And here A is the field F. With respect to our V1, V2, and V3, we get the null of T minus lambda 8i, which is equal to the eigenspace 8 T. It's just the linear combination of the first basis vector. Of course, you can, if you don't haven't followed that. So here, I would like to emphasize that if you get here T, and then you get A, B, C here, this is just equal to 8x, 8, not 8, 8a, 8, 5b, and then 5c. This is equal to 8 times a, b, c. Then this is only true is true when our b and c are 0. And here we have eigenvector a 0, 0 here. I noticed that here I write it downward and upward. And basically, it depends on the book or that you use. And of course, we can write this as a V1 and then 0 V2 and 0 V3. So this is just a V1. This is just a V1, and then our A is in F, which is basically span of V1. So I'm rewriting everything I did above again in other language here. Now for lambda equal to 5, we get how do you find it? In the language of linear maps, so we get T of A, B, C is equal to what is that? A, 5B, and then 5C is equal to 5 and then A, B, C. This is true when, of course, here we excluding 0 vector. This is true when your A is equal to 0. Okay. Thus, with respect to V1, V2, and V3, we get 0 and then B and then C. So this is just equal to, this is just, we have our eigenvector is just an element is of the form A V2 plus B V3, which is equal to the span of our V2 and V3. Thus, your eigenspace associated to 5 of the linear map defined above, linear operator is just the span of V2 and V3. Okay, so it may be good to check this. You can use other books or books that are giving more examples, computational examples, to get like a sense of how it's done. The next theorem, we will use this to prove. This is like the base theorem of, the theorem that will be used later on to the proof that we will be leaving because of the length of the proof, and then this is just the equivalence condition of what we call diagonalizable operator. So here we will state this as a theorem. You have a finite dimensional vector space, and then we have T, a linear operator, and of V, and then we have lambda1 to lambda m. We get these are distinct eigenvalues, and then the result is then your eigenvalue with respect to lambda1 plus up to eigenspace. This is eigenspace lambda m t is a direct sum. And furthermore, your dimension of E, let me remove this parenthesis, dimension of E lambda 1 T1 plus the dimension of E lambda m Tm is less than the dimension of our B, less than or equal to. This part here follows if this is direct sum, then this is a subspace, and then this is true because this is just a subspace of our finite dimensional vector space V. And then since this is a direct sum, there are no common component element except the zero vector. So let us prove this. So to show that this is a direct sum, suppose that u1 plus up to is equal to 0, and then each u sub j is in the eigenspace of lambda sub j in because the eigenvectors corresponding to the eigenvalues are linearly independent, since the vectors corresponding to the eigenvalues are linearly independent, then we get each of our u sub I, j is 0. Okay. Okay. Now using our previous theorem, being linearly independent, and then we get by our previous theorem, we get this one t up to, this is the representation by 0 as linear independence, and then the direct sum and linear independence theorem before. This is from theorem 144 in the mode book. Theorem 144 1.44. So this is basically saying that if you get a you want to use sub m subspaces such that u1 plus up to u sub m is a direct sum, this is only true if and only if we can write 0 as the sum of U1 to UM, where U sub j is in U sub j, and each U sub j is equal to 0. This follows. Now, going back to our theorem, we have we have uh, we have the needed result. This is the dimension now of our lambda E1 up to the dimension of E lambda M E is equal to the dimension of the direct sum. Wait, let me write this as this one, and then I from 1 to M, and then E, and then lambda I, and then T, which is basically equal to, which is this one. This one here is from the previous exercise. This is exercise 16. Let me check the exercise 16. From chapter 5. Exercise says that, oh, I got lost in the tracking of the exercise. Let me go back to C, going back to 2C, and then exercise 16. This is on dimension, and then it says that if you get subspaces of U1 to UM of finite dimensional vector space, and then U1 up to UM is a direct sum, then U sub 1 direct sum up to U sub M is finite dimensional subspace, and then this direct sum has dimension equal to the dimension, the sum of the dimension of each component. So this is, which is of course less than the dimension of the big space V. Okay, I think that's all for the theorem. Now we will introduce definition on the definition of another class of matrices. So this is called diagonalizable matrix. Let's define not a matrix but an operator P in the is diagonalizable or called diagonalizable if the operator has a diagonal matrix. And then we call the matrix, of course, diagonal matrix with respect to some basis of our vector space. Let us consider an example. T in LR2 defined as follows. We have xy here is equal to 41 x plus 7y, and then negative 20x plus 74y. Then the matrix with respect to T is given by 41, and then 7, and then negative 20, and then 74. Which is not diagonal matrix. Okay. Okay, it's not diagonal. with respect to standard basis. But what? T is diagonalizable because the matrix of T, but with respect to 1, 4, and then 7, 5, the matrix of T is, let us look at T of B1, of 1, 4. So this is 41 plus 7. How do you find the matrix of 1, 4 here? This is equal to 69, and then we get 69 times, this is the same as equal to the 1, 4 here plus blank 7, 5. So this is 69 and then 0. And then T of 7, 5, we get 0, 46. Oh, wait, 0, 1, 4, and then 46 times 7. Verify. We giving us matrix with respect to T. With respect to that basis, it's just 69, 0, and 0, 46. Okay. Let me now resuming our recording, we get T applied to our vector 1. This is our V1 and then V2 prime. This is also a basis for basis also of R2 because these two are linearly independent and there are only these two vectors, and R2 is two-dimensional, and then linear independent is which is linear independent is of length 2 is a basis. Now, if you apply T to our first basis element 1, 4, you get 69 plus 69 here come from 41 times 1 plus 7 times 4, and then 276 come from negative 20 times 1 plus 74 times 4. Here you get here when we input this. So basically, this is just equal to 69 times the vector v1 plus 0 that's vector v2 bar. And then T applied to the second basis vector prime is just 322 to 30. 322 here, apply your 7 and 5 to this one, you get 322, and then apply 7 and 5 to this one, you get 230. And then this is just 0 times v sub 1 bar plus 46 times v sub 2 bar, and hence we get the matrix of the linear map with respect to the basis vector, the new basis vector 1, 4, and 7, 5 is given by 69 and 46, which is this is a diagonal matrix. So here T is diagonalizable. Since we have found a basis such that the linear the matrix of the operator T with respect to that basis is a diagonal matrix. Okay. Let us continue with the pure equivalent conditions for diagonalizability. So here we get the V, finite dimensional, and then T, a linear operator on V, and then up to M, distinct, eigenvalues of our linear operator T. Then the following are equivalent. Letter A, we get T is diagonalizable. Diagonalizable. Letter B, we get V has a basis consisting, it follows, the A implies V follows from the previous theorem, eigenvectors of our T. See here, there exists one-dimensional subspace. There exists one-dimensional subspaces, not because there's many of them. There exists subspaces, we call that U1 up to U sub M of our V, and each is invariant under our T, such that your V is just the direct sum of U sub 1 and then up to U sub M. Okay, okay, let me write the dimension as N, the number here N, and then lastly, letter D, not last, D is just following here E, and then lambda 1 T, and then direct sum to lambda, the eigenspace of lambda M T, and then of course letter E, the dimension of our vector space V is just the sum of the dimension here of the dimension of the eigenspaces. Most of them are directly easily proven. For example, A and B are equivalent because for basis V1 to Vm of V, we have a diagonal matrix if and only if P of V sub j is equal to lambda sub j, V sub j for each j. So that's equivalent. And then the rest I will leave as reading exercise. So the proof here is left as reading exercise. It is found in the book, but it will like consume around maybe 15 to 20 minutes. Okay. So now we are going to use these equivalent theorems to show that now we get some theorem on diagonalizability of an operator. The question is, are there operators that are not diagonalizable? So the answer to that is yes. In fact, we will give an example of an operator that is not diagonalizable. The following is the example. So z given by z0. This is t is an element of linear operators, or the space of linear operators on the C2, or two-dimensional uh, two copies of C. This is the set of complex numbers. Okay. So how do you find this? So now this we have to show that T is not diagonalizable. Diagonalizable solution. We can form the matrix with respect to maybe the standard basis, or standard basis to some basis, some basis, standard basis. I'll use standard basis of our T. It's just 0, 0. Here, the first component is just mapped to 0, z. And then the second component is just up to 0, not z, but 1. Of course, easy to see that only 0 is the eigenvalue. All right. And then the eigenspace of 0 with respect to t. So what is unchanged here? So it's the null space of our t minus lambda I. So we get if w without respect to any w, we can this w is in C2. Here w is in set of complex numbers. So if you apply any vector of this form, we get the 0. We just have only vectors of this form is mapped by t to a multiple of z0. Okay, so now let's look at t of w0. This is just because 0 here, so regardless, how do you find it? This is just z0. So regardless of what value of z you get, and of w, you just have the vectors of w0 is an eigenvector with respect to the eigenvalue 0. I think you should also verify this, and then that is easy to see from the matrix. Now, there is a theorem on the distinct eigenvalues and then its relationship with diagonalizability of T. Here, if T has dim B, distinct eigenvalues, then our t here is diagonalizable. Diagonalizable, not conversely. Let us prove this theorem. So suppose t has dim v, it's eigenvalues. So for for each j, let us pull into dim v. For each j, let v, j be an element of v, the eigenvector with respect to the eigenvalue v sub j. Okay, the eigenvectors corresponding to distinct eigenvalues are linearly independent. Recall that v1 up to v dim v is linearly independent. And then if we have linearly independent, and then this is the dimension correspond to the dimension of v, then this one, there are dim v of them. So we get basis of our vectors space V. And then with respect to the consisting eigenvectors, we get, with respect to these bases of eigenvectors of eigenvectors, our previous statement here says that T is diagonalizable. Okay, we have T is diagonalizable, or T is diagonal. Yeah, you get what I mean. I'll just not write the full word. Now, how do you I'll give an example here. Let's consider, but not conversely. So I will show the converse later on. But let us consider an example first. So here, let us consider a map on F3, and then here x, y, z is mapped to 2x plus y, 5y plus 3z, and then 8z. And with respect to standard basis, we get the matrix of the transformation is given by 2, 1, 0, and then 0, 5, 3, and then 0, 0, 8. So here, how do you find this? This is x and y, so just correspond to this. 3 and z correspond to this, and then 8c correspond to this one. Okay. Now, here is this is upper triangular. And what can we do about this? We have the eigenvalues of t. The eigenvalues are 2, 5, and 8. So the goal here is to find basis because T is an operator on a vector space with 3 dimensions and has distinct eigenvalues. There exists a basis with respect to which T is diagonalizable. This is from the previous result on the determination of eigenvalues, theorem 5.30 44, that is from above. Here in the book, if it has let me recall it. If has dimension b distinct eigenvalues, then this one, the previous theorem, if it has dim b distinct eigenvalues, then t is diagonalizable. Here we get t, and then we have 1, 2, 3 eigenvalues. Then we conclude that this is a diagonalizable matrix with respect to some basis. And then the goal here, find the basis for which we get the diagonal matrix. All right, that's why I did not fully prove the statements above, because I want to illustrate this computational example. So to find the basis, we get now we have lambda equal to 2, 5, and 8. We get t of x, y, z, lambda of x, y, z. Okay. Okay. So how do you find that? All right. So here we have the matrix 2, 1, 0, 0, 5, 3, 0, 0, 8. We get x, y, z here. And then we get first, for lambda equal to 2, we get 2 x, y, z. So for the first one, we get 2x plus y equal to 2x. And then 5y plus 3z, we get 2z, 2y. And then we get 8z equal to 2z. This means, what value do we have? So this means that our z is 0. And then here, your y is equal to 0. And then since y is equal to 0, we will make x our free variable. We get eigenvector of form x 0, 0. So take v1, v1, 0, 0. Okay. Also, for lambda equal to 5, with the same reasoning, we get 2x plus y is equal to 5x, and then 5y plus 3z is equal to 5y, and then 8z is equal to 5z. So this means that what? This is 3x minus y equal to 0. And this one, this is 5. Here we get z equal to 0. And here we get the same. So we have, if we get x to be free, then our y is 3x, and then z is 0. Okay. So eigenvector is of this form. So we can factor out the x here. We get 1, 3, 0. So we can consider this as another basis. V take V to be 1, 0. And also for 8, we get the same. 2x plus y is equal to 8x. 5y plus 3z is equal to 8y. And then 8z is equal to 8z. So we have z here. How do we find this? Z is equal to, so from here we get, let's make this one is, what's this? 8 minus 2 is 6, x equal to y. So let's fix, and here we get, this means that our 5 minus y, 8 minus 5 is 3y. 3y is equal to 3z. So here y is equal to z. This means y is equal to z. Thus, we get 6 here. If we have x here is our first component, then your y is 6x. And then your z is also 6x. And thus giving us, if we factor out x, 166. So V3 is equal to 166. So this will be our eigenvector for our lambda equal to 8. So here we have for lambda 1, lambda 2, lambda 3. So lambda 1 is 2, this is 5, this is 8. There's corresponding V1 here, V2, and V3 is V1 is 100, and then this the other one is 130, and then the other one is 166. How do we compute the basic the matrix with respect to this vector? So, all right. There's a lot of computation here. So, for example, if this is our map 100, this is just the first component is 2x plus y. So 2x, 2 times 1, so 2 here, and then the rest are 0, 0. This is just 2 times our v1 plus 0 v2, and then plus 0 v3, and then p of 130, we get first one is 2 times 1 plus 3, 2 times 1 plus 3. 2 times, okay, wait. 2 times 1. Where's the linear map? The linear map is 2 times x plus y. P of x, y, z. Let me write 2 times x plus y, and then the other one is 5y plus 3z, and then 8z. So for this is 2 times 2 times 1, 2 plus 3. This is 5. And the other one, 5 times 3 is 15. So 15. And then the other one is 8 times 0. This is just equal to 0. And then V1 plus 5 times V2 plus 0 times V3. So 5 times V2 is, yeah, 5 times 1. And lastly, this is T of 166. This is 1. Can you supply this one? So it will give you 0 V1 plus 0 V2 plus 0 8 V3. So that with respect to let's call this bar to V1, V2 bar, and V3 bar, our basis of what is this? F3. We have matrix. The transformation is given by 2, 0, 0. So here is 2, 0, 0. So 2, 0, 0. This one is 2, 0, 0. So this is 2, 0, 0. 0, 0, 5. So this comes here, and here this comes at this side. So here we get 5 and 0, and then this is 0, 8. And then this is diagonal matrix. So T is diagonalizable operator. And then the converse, we can the converse is the following. Let us consider the map given by T of Z1, Z2, Z3. This is just map to 4Z1, 4Z2, and then 5Z3. The corresponding with respect to the standard basis, you get the matrix is just 4, 0, 0, and then you have 0, 4, 0. Then we get 0, 0, 5. So we have 2, only 2, only 2, which is just strictly less than dim v. Dim v is equal to 5, not 5, is equal to 3. Dim v is 3, so only 2 here, only 2 eigenvalues, but T is diagonalizable. So diagonalizable. Okay, so we get what? A counterexample that even though we have not dim v number of eigenvalues, we also can get a we have a diagonalizable operator. So the converse is not true. So in later video, we will find conditions that imply how to tell whether the operators are diagonalizable or not. So for now, I think this will be the end of this recording, I find it hard to work with the computational examples, even theory. But yeah, get stuck from time to time. So my advice is just take time with it when you are studying linear algebra or any math, and then yeah, it will make sense by asking many sources or references. And if it's not clear in one book, or you can use another book, and then be sure to match the development. And then maybe if you can have the access, there are softwares, or maybe artificial chat GPT, or whatever kinds of AI that will give you some references. But be sure to check this on, of course, your own understanding. So if there's something wrong, then you can, if you have some exposure to it, you may can detect it. Now let me end this. This is the end of uh our chapter 5. So chapter 5 basically deals with what is the chapter 5? Chapter 5 is on eigenvalues section, or chapter on eigenvalues, eigenvectors. Next video, next we'll be covering chapter 6, which the topics for chapter 6 is inner products. So inner products is something like if we have encountered vector or dot product. And so this is just some more generalizations of that concept. So I think that's all for this video. Yeah, that's the end.